How would I search it to find the best solution? So I'm going to do the following. Here's a piece of code that does a depth-first search on a decision tree. It's got a route into a decision tree. It's going to have a very similar structure to before. Again, I'm going to have some function that tells me something about what I'm trying to accomplish. But I'm going to need a second function here called a constraint function. All right, let's look at the structure of it. As before, I'm starting off with a stack that's going to keep track of what portions of the tree to explore. And it's going to begin with the root node in it. I'm going to keep track of how many nodes I've visited because I'm going to print that out at the end down here. And that's just something to let me see what goes on here. And I'm going to set up my best solution so far initially to be none because I haven't seen anything. Structure is very similar to before. I'm running through a while loop. As long as I've got something in the queue to look at, I'm going to do something here. But the first thing I'm going to do is I'm going to check to see, do I still have room? So constraint function basically says, given the first element in the stack and its value there, the constraint function will tell me, can I add it in? Okay? If I can, in fact, add it in, I still got room to add it in, then if I've not yet found a solution, I'm going to set best to be the solution I have at this point in the stack, because this is a good solution. If, in fact, I already have found a solution, then I'm going to check to see, does this one do better? So I'm going to call my value function on the values at this element and compare it to what I get on the best solution so far. I'm using get value to get out the value of the actual thing stored in here. And based on that, if, in fact, that is better, then I'm going to send best to this point in the stack. So this is just using my evaluation function to say, do I have something better than what I've seen so far? And if I do, keep track of it. I'm still exploring the tree. So there's one change. After that, the difference is just, add to the queue, just like we did before. So I'm again just exploring this opportunity, and I realize right here, this should actually not be stack. It should be, sorry, that's a typo, stack.pop of 0. I'm popping it off. The other difference is that if, in fact, the constraint function didn't hold, there was no opportunity to put anything in, I don't need to continue looking at the tree. I can just drop it, and I simply pop the stack and continue on. And when I'm done with all of this, I return my best solution. So it has the same kind of structure as exploring a tree. All I'm doing that's different here is, in this previous case, I was just checking to see, do I have the value I'm looking for? Here, I'm checking to see, can I still add something in? And if I can, do I actually get a better value as I do it? There's a depth-first version of it. We can do exactly the same thing with breadth-first. So you can look at this. Again, this is a slight bug. No, it isn't a bug. I've got it done right there. Sorry, there's the pop. It's exactly the same, except I'm using a queue rather than a stack, and so the ordering here is different. I'm appending it to the end rather than putting it at the front. Otherwise, it's exactly the same. Okay, let's look at an example. So here's a simple little example. My elements here are a value and a weight. And I should really build an object out of it, but I'm just using it as a list. So I got 4 little elements here. I can actually build a tree by using my build tree. Again, I start off with nothing so far and the set of things to build. I'm going to call that tree test. I will need, in order to explore it, 2 things. One is, what's the thing I'm trying to maximize? So I've got a little function here, or procedure called SumValues, that simply gets me out the first elements, or the values, if you like, these pieces of all the things in a list, adds them up. And I need to have a constraint. And so I'm going to do a similar thing, adding up the weights of the things in it and making sure in this case that it's less than 10, that it's got a weight less than 10. It could be anything arbitrary. Let's look at what happens if I run it. So in fact, I can come over here and say, if I want to run this, I'm going to call foo, just for arbitrary sake, to be the depth first search of a D tree. I'm going to use my tree test as the example. And SumValues, because I want to add up the value of the things there, and I'm going to ask that the weights be below 10. And in my code over here, I'm actually going to print out every time I find a better solution, what do I find? So it works its way through the tree. The initial one is empty, of course, and then it says, I can add in the thing worth 6, which is A, and then I'm going to try and add in the thing worth 7, and then I'm going to try and add the thing worth 8, which was good. All of those would fit. But in fact, eventually I find out that there's a better solution if I take that last one out and add in the thing worth 9. And that gives me something that still fits and gives me a better solution. And visited 31 nodes. Okay? I could do the same thing as I deal with all of that, and in fact, if I wanted to look at it, I could simply say, just to check it, what's the value here? Okay, and there it is. And so in fact, I realized I was wrong. It tried to add in this 951 and couldn't fit it because it wouldn't fit in. It wasn't there below 10. And so it gives me out a solution that I want to get out there. I could do the same thing with breadth first search. And again, it's going to print out a set of things, and it returns out an object when I'm done with it. And notice it also visited 31 nodes as it went through here. So the idea here is that I've built the tree. I can now explore it, breadth first or depth first, and I can find a solution that tells me when I get to that point, here's actually the set of decisions you want to make to maximize this particular object or this particular objective function. And in the next segment, we're going to look at a variation on that.